Okay, good morning, afternoon or evening, whatever the time of day is that you're watching this, and welcome to Professor Tietjen's sort of end of module pub quiz. So this will be a multiple choice question quiz consisting of, I've forgotten how many, I think 13 questions. I think so. If you want to replicate the normal conditions that I use for a quiz like this, if we were in your lecture, then you can time yourself between each question, give yourself 30 seconds. You'll need to pause the video in between questions because I will just be moving from one to another to another. I'm not just going to sit here in silence for 30 seconds whilst you think about it. You can pause yourself, or pause the video I should say, and time yourself for 30 seconds if you want, or 60 seconds, or however long you think you need. But 30 seconds is what I would usually use, or alternatively you could just look the answers up online, which is cheating, and I will find out who cheated. Normally there'd be a prize, but well, there we go. Anyway, so if you want to pause now and grab yourself a pen and paper, then we will begin. Obviously, we're going to discuss the answers afterwards and have a bit of a chat about them. So, as is tradition, question 1. What are the 3 planes of movement? What are the 3 planes of movement? Are they A, transverse, mediolateral, contralateral; B, sagittal, frontal, coronal; C, transverse, contralateral, sagittal; D, transverse, sagittal, frontal. So pause here, give yourself as much time as you need, and then we'll move on to question 2. Okay. What does the word isokinetic mean? What does the word isokinetic mean? Is it A, constant torque; B, constant angular acceleration; C, constant angular velocity; or D, constant angular momentum? Again, pause, have a think, and we'll move on to the next question. Here we go, question 3. Which of the following kinematic features is not typically observed during barefoot running? So that's in comparison to shod running. Is it A, increased dorsiflexion; B, increased cadence; C, increased plantar flexion; or D, increased knee flexion? So which of those options is not typically observed when barefoot running? Okay, question 4. Which of the following is the most accurate definition for moment of inertia? And I say most accurate because technically there are going to be more than one definition here that apply, or definitions that apply, but it's your job to pick the most accurate one. So is it A, an object's resistance to angular acceleration; B, an object's resistance to angular deceleration; C, an object's resistance to angular impulse; or D, an object's resistance to angular momentum? Okay, moving on to the next question. What does degrees of freedom mean? What does degrees of freedom mean? Is it A, the number of planes of motion you can measure during a motion analysis, so using a 2D camera; B, the numbers of pieces of information you have to describe an object's movement; C, the numbers of pieces of information you have to describe an object's power output; Or D, the number of ground reaction forces you can measure during a force plate analysis. Okay, moving on. Which of the following are we not able to assess using surface electromyography? Oh, sorry, which of the following are we able to assess? Not able, which of the following are we able to assess using surface electromyography? My apologies. A, muscular force. B, muscular power. C, neuromuscular activity. D, neuromuscular innervation. So which of those are we able to assess using surface electromyography? Okay, moving on to your next and my favourite question. Some of you might have come across this one before, but still, I'd like to include it. Which of the following is Manos's favourite lunchtime meal? Is it A, spanakopita with cubed feta? B, fasolada soup. Don't know why I have to do the accent, I just do. C, sun-dried octopus. D, wet bread. And just to, I don't know, give this an element of reality, and just so you're not misled, at one point or another he has eaten all four of those for lunch in the office, hence why I try and work from home as often as possible now. But which has he eaten the most? Which do I tend to walk into the kitchen and see him snacking away on? Okay, moving on. Which of the following skeletal muscles cannot be assessed using surface electromyography? A, the vastus lateralis. B, vastus intermedius. C, vastus medialis. And D, biceps femoris. I will give a bonus point if you can then also tell me why that particular muscle cannot be assessed using surface electromyography. Moving on then to your next question. It says, there it is. Which of the following are ways of assessing kinetics in sport and exercise biomechanics? So this hinges on your understanding of the word kinetics. A, force plate and 2D motion analysis. B, isokinetic dynamometry and surface electromyography. C, 2D motion analysis and surface electromyography. D, force plate and isokinetic dynamometry. Two of those are considered kinetic measures of, or kinetic research techniques. Which are they? Okay, moving on. Which of the following is considered a limitation of isokinetic dynamometry? There's only one. Which is it? A, poor external validity. B, poor internal validity. C, poor repeatability. D, poor objectivity. Let's move on. Place these motions in order from least to most difficult to assess using 2D motion analysis. So try to imagine that you've got a 2D motion capture camera. You're just trying to record one of these motions using your mobile phone. And put them in order from easiest to hardest to assess accurately. A, head rotation. B, hip flexion. C, shoulder abduction. D, forearm pronation. Oh, there it is. Help if it was there. Okay, moving on. Which of the following are considered strengths of 2D motion analysis? So there will be more than one correct answer here, and there will be more than 4 options to choose from. A, it has good good external validity. B, it's more practical than 3D motion analysis. C, it's more accurate than 3D motion analysis. D, it's easy to combine with other research techniques. E, minimizes the Hawthorne effect. F, it can assess movements in 6 degrees of freedom. So again, more than one right answer there. Which of those options is it? Okay, and your final question. Which of the following is not true of barefoot running? So which of the following is not true of barefoot running? A, it's more natural than shod running and therefore causes less injuries. B, it typically causes the runner to adopt a forefoot strike pattern. C, it results in an increased running cadence. D, it reduces the incidence of overstepping or the overstepping gait. So which of those is not true of barefoot running? Take your time, answer the question, and then we will go through and discuss the answers. Okay, so let's go through the answers then. Question 1 was, what are the 3 planes of movement? So a nice little introductory question here. And the answer was D, the transverse, sagittal and frontal planes of movement. So fairly straightforward. Transverse motion, or movement that occurs in the transverse plane, is usually rotation. So this would be something like, say, head rotation, looking from left to right, or trunk rotation, twisting your trunk from side to side. Movements in the sagittal plane are usually flexion and extension movements, so flexing, extending your elbows, arms, elbows, shoulder, hip, knees, ankles, lots of options there. Frontal movements typically include abduction and adduction. Option A, mediolateral is a ground direction force, and contralateral refers to the opposite limb of reference. So if we're looking at someone running and we are referring to their right limb, let's say, as their stance limb, the contralateral limb would be the other limb that's in the swing phase. B was a bit of a trick one. Frontal and coronal are both terms that are used for the same plane of motion. Coronal was the original term for the frontal plane, but these days people tend to use frontal plane more often than coronal, but they mean the same thing. And again, in option C, contralateral just isn't a plane of motion. So your answer there is D, because they are all actually planes of motion. Okay, moving on to our next question, which was, what does the word isokinetic mean? The answer is, drum roll, and the answer was C, constant angular velocity. It's a confusing term. Iso refers to constant, singular. Kinetic in biomechanics refers to forces. So that could be a torque or a force, which produce angular or linear motion respectively. So the term isokinetic is somewhat misleading, because kinetic doesn't refer to velocity. But for some reason this is a term that we've just not changed because that was the original definition that was given, and we've just accepted it that okay, it's not actually accurate, but it's better than going and rewriting all those textbooks. So technically constant torque would be correct, but it isn't. It's constant angular velocity. Technically B, constant angular acceleration, means the same as constant angular velocity. If acceleration is constant, then angular velocity is constant, but velocity is more accurate, and so too with angular momentum. Technically they all mean the same thing, but again velocity is the most accurate. So question 3 was, which of the following kinematic features is not observed or typically observed during barefoot running? And I use the word typically in there because sometimes people will deviate from this, but the answer is A, increased dorsiflexion. When we take our shoes off, we tend to adopt a forefoot running style. Not always though, so hence why I put the qualifier in there of typically. But we tend to adopt a forefoot running style, which means we are plantar flexing our foot to land with the forefoot first. So the forefoot contacts the ground and the heel, and we push off from that position. Because of the time that it takes to bring the foot into contact with the ground with a forefoot strike, so forefoot, rear foot, and then reversing that to push off, this results in a reduced stride length, which increases cadence, that's the number of steps per minute, and step length and stride length are reduced because knee flexion is increased. So as I demonstrated during your lecture some time ago, it's almost like prancing like a deer from one foot to another. So we don't usually see an increase in dorsiflexion, although it's not unheard of, but not typically. Okay, so your next question was, which of the following is the most accurate definition for moment of inertia? Moment of inertia is defined, if you like, in terms of an equation by the mass times the radius squared of that mass. So the equation would be written in shorthand as I, capital I, equals m multiplied by r squared. So we're referring to mass here and its distance from the axis of rotation. And if you think back to linear motion, inertia is an object's resistance to acceleration. Therefore, the answer to our question is A, an object's resistance to angular acceleration. Simply how much an object resists being moved in an angular motion. B, an object's resistance to angular deceleration, refers to angular momentum. C, an object's resistance to angular impulse, could also technically count because the impulse would cause the acceleration, but angular acceleration is more accurate. And D, an object's resistance to angular momentum. The momentum would come as a product of the impulse and acceleration. Therefore, A is our correct answer. Okay, our next question was, what does the phrase degrees of freedom mean? So this is a term that we use in motion analysis. And the correct answer was, drumroll, B. A degree of freedom is a piece of information you have to describe an object's movement. So if you could only assess an object's movement in one direction, let's say just from left to right, you would have 1 degree of freedom. If you could also assess its movement up and down, you would have 2 degrees of freedom. You see where I'm going with this? If you could assess its movement left, right, up, down, and backwards and forwards, you would have 3. You could then also assess an object's rotation in 3 degrees of freedom as well. So the maximum is 6. So 3 linear movements, up and down, left and right, backwards, forwards, and 3 angular movements would be rotation in those 3 different directions. So the number of planes in motion you measure during the analysis A is just wrong. The number of pieces of information you have to describe an object's power output, again, just wrong. As is D. There's no real explanation needed here. It's simply the number of pieces of information you have to describe an object's movement. Degrees of freedom also abbreviated to DOF, D-O-F. Okay, so our next question was, which of the following are we able to assess with surface electromyography? The answer is C, neuromuscular activity, or in the simplest possible terms, you could say muscular effort. It is the variable that results in force production. So neuromuscular activity refers to the recruitment of motor units, and those motor units produce force. Therefore, muscular force is not the correct answer, and that's very important to remember. I've put this one in here deliberately because they do not measure muscular force, or we do not measure muscular force with EMGs. But many people still make this misconception. Force is the product, power is the product of force multiplied by velocity, so also incorrect would be B, muscular power. And D, neuromuscular innervation, refers to the nerve supply into the muscle. If a tissue has a nervous supply, then it is considered to be innervated. So, for example, the connective tissue in your joints, the cartilage and the menisci in your knee, they do not contain a nervous supply for obvious reasons. Who wants to feel every time your joints are rubbing against each other? However, bones, muscles, your connective tissue that holds your skin together is all innervated. So that is a tissue that is innervated. So the correct answer is C, neuromuscular activity. Okay, your next question was, which of the following is Manos' favourite lunchtime meal? The answer is wet bread. Yes. So he has had all of these other options in the past. Sun-dried octopus, he had just the once because everyone moaned. Fasolada soup is the traditional soup, which I tried and actually wasn't that bad. Spanetta coppita with cubed feta is kind of like, again, a traditional salady sort of thing. I don't know. He had it once. He's always offering me things I don't want. But wet bread, he will get 2 slices of Hovis, sit them on a plate, run the tap over them, leave them for a minute or two, because apparently it aids his digestion of starch. He supposedly struggles to digest starch, and this helps. Moving on. Which of the following skeletal muscles cannot be assessed using electromyography? And bonus question, why? The answer is drum roll, the vastus intermedius. And the reason why is because it is deep to the other quadriceps muscles. That means that the vastus lateralis, the vastus medialis, and the rectus femoris, which admittedly wasn't an option here, all cover the intermedius. And surface electromyography, as we know, involves attaching sensors to the skin, and you measure the activity of what is directly beneath them. So the lateralis and the medialis, being your lateral and medial quadriceps, they aren't so much in the way. It's the rectus femoris which gets in the way of the intermedius. It completely covers it. There has been one or two papers I think I've seen over the years that have said, no, you can assess intermedius activity, but I fail to see how. I don't personally believe it. The biceps femoris is one of your three hamstring muscles. It's your outermost hamstring, and that too is superficial. You could easily assess that. It's not an issue. So the answer is the intermedius, because it is deep. The other muscles are superficial muscles. They're near the surface of the skin. Okay, our next question was, which of the following are ways of assessing kinetics in sport and exercise biomechanics? Oh, excuse me, got a sneeze. Oh, there we are, all better. So this question obviously depends on your definition of the word kinetics. Kinetics simply refers to forces, whether they are linear or angular. So the correct answer here was D. Force plate analysis, which measures ground reaction forces, and isokinetic dynamometry, which measures torque, which is a rotational force around our joints. Option A, 2D motion analysis, that is a measure of kinematics. B, again, dynamometry is fine, but surface electromyography doesn't measure force. And C is wrong for the reasons I've just given. So the answer is D. Force plate analysis and isokinetic dynamometry. Linear and angular kinetics. Okay, so your next question was, which of the following is considered a limitation of isokinetic dynamometry? The answer is A. Poor external validity. You could rearrange that to say poor sport specificity. External validity refers to the validity of the data that you collect from any research technique to the real world, to sport-specific conditions in this case. And as we've said before, dynamometry has virtually zero sport specificity, or more specifically, external validity. It does, however, have excellent internal validity, which refers to basically how good or how valid is the data that you collect using a particular research technique. How good is it at doing its job, basically. It's very good. It does it very, very well. It's the gold standard for measuring joint function. It's very easily repeated. You can easily get someone back in the lab, reset the chair, and the dynamometer head to the exact same position they were in the last time they visited the lab, and it is perfectly objective. There is an element of subjectivity in there, of course, but because it's objective, we're applying numerical data to it. Therefore, this technique has good objectivity. Were it to be subjective, we would say, well, this is something that is more a matter of opinion, something that doesn't have a numerical outcome, more like a manual muscle test. So A, poor external validity, brackets, poor sport specificity. It is the great limitation of isokinetic dynamometry, and I find it, as I've said before, interesting as we progress. I've often pondered this and discussed it with, Stuart, the only one who listened to me, as to whether dynamometry will still even exist in years to come. It's because of this reason. It's a great technique and I really like it, but given that it's virtually useless at relating it to the real world, is the internal validity enough to make up for that? And that is indeed the subject of your short answer question, or at least one of them. Okay, so your next question, well, not so much question but task, was to place the motions that were listed below in order from least to most difficult to assess using 2D motion analysis. And the answer is, you can have a point if you like for each correct one. Hip flexion would be super duper easy. You've done this yourself in your research project for your report assessment. Shoulder abduction, marginally more challenging, only because as I've shown in, if you go back to your lecture slide where we talked about 2D motion analysis, the movement of the humerus relative to the scapula is hard to assess using any motion analysis technique, because you can't physically get under there and attach a marker to bone. You can just attach it to the skin. So whilst it's arguably just as easy, it's not necessarily going to be as accurate, so that's in at number 2. Head rotation is not too bad. You would have to position the camera above the participant, looking down. Ideally they'd wear a headband with 2 markers on the left and right hand side of their temple. It's easy enough if they're sitting still, however it becomes far more challenging if they're moving. And forearm pronation would be the most challenging. The best way I've found of doing it over the years is actually to get the participant to grab a long pencil or a pen and actually put markers on the end, on either end I should say, of the pen, and then get them to rotate their wrist from pronation to supination and record that. The other complicating factor is that if you hold your arm out directly in front of you and pronate and supinate your wrist, there is also the factor that your shoulder is rotating. So to try and minimize this, we would have to get our participant to keep our arm flexed at, or keep their arm flexed at 90 degrees, so that we're just assessing pronation at the wrist. Without using the pen, it becomes very tricky, because it's a case of, well, where do you put the marker, or markers I should say. So hip flexion, shoulder abduction, head rotation, forearm pronation. 1 point for each correct answer. Okay, so our next question was, which of the following are strengths of 2D motion analysis? And our answers were, or correct answers were, that it has good external validity. Again, it would help if you compared this to 3D motion analysis. You can take a 2D camera out into the field and collect data, therefore the data that you get is more relatable to that sport. Therefore it's more practical, and by practical I mean just it's easy to use. You can pick up a camera, grab a laptop and go out to a hockey pitch or football pitch or wherever, whereas it's it's more challenging to take out 3D cameras. It's fairly obvious, I should think. And it is very easy to combine with other research techniques. It combines very well with the force plate and with the EMGs, which if you choose biomechanics next year we will do. More so with the 3D analysis, but it combines very well with other research techniques. It's certainly not more accurate than 3D motion analysis. It can be as accurate for measuring some movements, but generally 3D is preferred because it has 6 degrees of freedom, whereas 2D motion analysis only has 3. So there's why F isn't correct, because 2D motion analysis can assess 3 degrees of freedom, movement in 3 directions, so up and down, left and right, and one type of rotation. The Hawthorne effect is, as we've discussed, the phenomenon that occurs when someone is watching you move. You will change your movement pattern. We've all experienced this if we've, I don't know, seen, I don't know, someone who we find attractive, and we might walk with, I don't know, maybe more of a seductive gait, to put this in biomechanical terms, if we know they're watching. Likewise, you might change your movement pattern if you see someone who you don't want to meet. You might quickly jog past them. Someone watching you will instantly alter how you move. And then, unfortunately, 2D motion analysis actually increases the Hawthorne effect rather than decreasing it. And your final question, whoops, skipped ahead. Which of the following is not true of barefoot running? It's more natural and therefore less injurious. Rubbish. It's not more natural. There's nothing more natural about it. To say it's more natural would be to compare us to our prehistoric ancestors, but we're not living in those times now. So it's more natural for them. It's not more natural for us. We live in a world of concrete. So for us, running barefoot is not more natural. And that is basically our reason why A is not accurate. It does, as we've discussed, cause our runner to adopt a forefoot strike pattern. It results in increased cadence. Overstepping refers to excessive hip flexion knee extension when running. There's a nice image of this on the lecture slides where we talked about this. We talked about running barefoot shod. And if anything, barefoot running is going to reduce the incidence because it causes us to run with increased knee flexion. Okay, so hopefully that was useful, and hopefully you got all of them right. If there are any questions, do feel free to email me, and keep up the good work.